For most of human history, the universe appeared calm, orderly, and predictable. Stars moved across the sky in fixed patterns. Planets followed steady paths. Gravity was understood as a gentle force, one that kept the moon in orbit and apples falling to the ground. Nothing about gravity suggested it could become violent, destructive, or absolute, yet hidden within gravity was a terrifying possibility. The idea that gravity could become so strong that nothing, not even light, could escape was unthinkable for centuries. It challenged intuition, common sense, and even the limits of imagination. And yet this idea would eventually become one of the most important discoveries in modern science. The discovery of black holes did not begin with telescopes or space missions. It began with mathematics. In November 1915, Albert Einstein completed and presented his theory of general relativity in Berlin. This theory fundamentally changed humanity's understanding of gravity. Instead of treating gravity as a force acting at a distance, Einstein described gravity as the curvature of space and time itself. Space and time were no longer separate, they formed a single fabric, space-time. According to Einstein's equations, massive objects like stars and planets bend space-time around them. The more massive the object, the more extreme the curvature. Einstein's equations were powerful and dangerous. They allowed physicists to imagine scenarios far beyond everyday experience. What would happen if a massive object collapsed into a very small volume? What if space-time curved so sharply that nothing could escape? Einstein himself did not believe such extreme outcomes would occur in nature, but his equations did not agree. In January 1916, while serving as an artillery officer during World War I, a German physicist named Karl Schwarzschild found an exact solution to Einstein's equations. Schwarzschild had received Einstein's paper only months earlier. From the front lines, he worked out a solution that described space-time around a perfectly spherical, non-rotating mass. What he discovered was shocking. Schwarzschild's solution predicted a boundary at a specific radius. Inside this boundary, gravity would become infinite. Escape would be impossible. Even light would be trapped. This boundary later became known as the Schwarzschild radius, what we now call the event horizon of a black hole. Schwarzschild sent his solution to Einstein in a letter dated January 13, 1916. Einstein was impressed by the mathematics but deeply uncomfortable with the implications. He believed the solution was physically unrealistic, a mathematical oddity, not something that could exist in the real universe. For decades, most scientists agreed with Einstein. The idea of a collapsed star that traps light was considered absurd. Nature, they believed, would always find a way to prevent such extremes. Black holes at this stage were not called black holes. They were referred to as frozen stars or gravitational singularities, and most physicists hoped they would remain theoretical curiosities. That hope did not survive the study of stars. By the early 20th century, astronomers had begun to understand how stars generate energy. Stars shine because nuclear fusion occurs in their cores. Hydrogen atoms fuse into helium, releasing enormous amounts of energy. This energy pushes outward, balancing the inward pull of gravity. But fusion does not last forever. When a star exhausts its nuclear fuel, the outward pressure weakens. Gravity begins to dominate. For stars with masses similar to the Sun, the collapse is relatively gentle. The star sheds its outer layers, leaving behind a dense core known as a white dwarf. For slightly more massive stars, the core collapses into a neutron star, an object so dense that protons and electrons merge into neutrons. But what about stars that are even more massive? This question haunted physicists. In 1939, J. Robert Oppenheimer and his student Hartland Snyder published a paper titled On Continued Gravitational Contraction. In this work, they explored what happens when a massive star collapses under its own gravity. Their conclusion was radical. If a star is massive enough, no known force can stop its collapse. Not electron pressure, not neutron pressure, not radiation. The star collapses endlessly, shrinking toward infinite density. From the outside, the collapsing star would appear to freeze as it approaches its Schwarzschild radius. From the inside, collapse would continue without limit. This was the first rigorous description of what we now call a black hole, yet even this did not convince the scientific community. World War II interrupted theoretical physics. Oppenheimer went on to lead the Manhattan Project. The study of gravitational collapse faded into the background. For another 20 years, black holes were largely ignored. Then astronomy changed forever. In the 1950s and early 1960s, scientists began observing the universe using new wavelengths of light. Radio astronomy revealed invisible structures. X-ray detectors showed intense sources of energy never before imagined. The universe was no longer quiet. It was violent, explosive, extreme. In 1964, astronomers detected a powerful X-ray source in the constellation Cygnus. This source was later named Cygnus X1. It emitted enormous amounts of energy, yet it was invisible in optical light. Careful measurements showed that Cygnus X1 was part of a binary star system. It orbited a massive blue star, pulling gas away from it. As this gas spiraled inward, it heated to millions of degrees, emitting X-rays, but the object doing the pulling could not be seen. Its mass was estimated to be more than 15 times the mass of the Sun. That was too large to be a neutron star, yet it emitted no light. This matched the theoretical predictions of a black hole perfectly. By 1971, Cygnus X1 was widely accepted as the first strong black hole candidate. Around the same time, physicist John Wheeler introduced a name that captured the imagination of the world: black hole. The name stuck. What had once been an uncomfortable idea was now unavoidable. Black holes were real, and they were far stranger than anyone had expected. By the early 1970s, black holes were no longer dismissed as mathematical fantasies. They had crossed a crucial boundary in science from theory into reality. Astronomers now accepted that black holes existed, but this acceptance immediately raised new and even more profound questions. If black holes were real, how common were they? How big could they get? And what did they mean for the structure of the universe itself? The first confirmed black hole candidates, like Cygnus X1, belonged to a class now known as stellar mass black holes. These formed from the collapse of massive stars and typically contained between 5 and several dozen times the mass of the Sun. They were extreme but still small on a cosmic scale. What truly shocked astronomers was the realization that much larger black holes existed, objects so massive that their gravity shaped entire galaxies. Evidence for these giants began to appear in the 1960s, when astronomers discovered quasars. Quasars were incredibly bright points of light located at immense distances, often billions of light years away. Some quasars emitted more energy than entire galaxies, yet they appeared to come from regions no larger than our solar system. The energy output was staggering. No known physical process could explain such luminosity except one: accretion onto a supermassive black hole. As gas and dust fall toward a black hole, they do not fall straight. Instead, they form a rapidly spinning accretion disk. Friction and gravitational forces heat this material to extreme temperatures, converting mass into energy with extraordinary efficiency. In fact, accretion onto a black hole can be more efficient than nuclear fusion. By the early 1970s, astronomers increasingly concluded that quasars were powered by supermassive black holes at the centers of distant galaxies. This led to a revolutionary idea. Black holes were not rare cosmic accidents, they were fundamental components of galaxies. In the decades that followed, evidence accumulated rapidly. Astronomers tracked the motion of stars near galactic centers and found that they orbited invisible objects with enormous mass packed into incredibly small regions. Our own galaxy provided one of the clearest examples. At the center of the Milky Way lies a compact radio source known as Sagittarius A. Beginning in the late 1990s, teams of astronomers carefully monitored the motion of stars near this region. These stars moved at astonishing speeds, some completing orbits in just a few years. Using precise measurements, scientists calculated the mass of the object they were orbiting. The result was undeniable: about 4 million times the mass of the Sun, confined to a region smaller than our solar system. There was no plausible explanation other than a supermassive black hole. By the early 2000s, astronomers concluded that nearly every large galaxy contains a supermassive black hole at its center. These black holes appear to grow alongside their host galaxies, influencing star formation, galactic structure, and even the distribution of matter across the universe. Black holes, once thought to be destructive anomalies, were now understood as architects of cosmic order. As observational evidence strengthened, theoretical physicists pushed deeper into the nature of black holes themselves, especially the strange behavior of space and time near them. Einstein's theory of general relativity predicts that time does not flow at the same rate everywhere. The stronger the gravitational field, the slower time passes. This effect, known as gravitational time dilation, becomes extreme near a black hole. To a distant observer, an object falling toward a black hole appears to slow down as it approaches the event horizon. Its light becomes redder and fainter, stretched by gravity, until it seems to freeze in place. But for the falling object itself, time continues normally. It crosses the event horizon without noticing anything special. This leads to one of the most unsettling ideas in modern physics. The event horizon is not a physical surface. It is a boundary in spacetime. Crossing it does not involve a shock or barrier, only the realization that escape is no longer possible. Inside the event horizon, the structure of spacetime changes completely. All possible paths lead inward toward the singularity. Just as we cannot stop time from moving forward, anything inside the event horizon cannot avoid moving toward the center. At the singularity, according to classical general relativity, density becomes infinite and spacetime curvature becomes infinite as well. The laws of physics, as we currently understand them, break down completely. This breakdown troubled physicists. Infinite quantities usually signal that a theory is incomplete. By the 1970s, it became clear that understanding black holes would require combining general relativity with quantum mechanics, the two pillars of modern physics that famously resist unification. This realization led to one of the most surprising discoveries in the history of science. In 1974, physicist Stephen Hawking applied quantum field theory to the region just outside a black hole's event horizon. What he found contradicted everything scientists believed about black holes. According to Hawking's calculations, black holes are not perfectly black. They emit radiation. This radiation arises from quantum fluctuations in empty space. Particle-antiparticle pairs constantly appear and disappear everywhere in the universe. Near an event horizon, one particle can fall into the black hole while the other escapes, carrying energy away. From the outside, the black hole appears to lose mass. This phenomenon became known as Hawking radiation. The implications were enormous. Black holes, once thought to be eternal, could slowly evaporate over unimaginably long timescales, far longer than the current age of the universe. A black hole could completely disappear. Hawking radiation connected black holes to thermodynamics. Black holes were found to have temperature, entropy, and energy. This was astonishing. Objects defined by gravity alone suddenly behaved like physical systems with microscopic states. But Hawking's discovery created a new paradox, one that remains unsolved. According to quantum mechanics, information cannot be destroyed. The complete description of a physical system must always be preserved. But if a black hole evaporates completely, what happens to the information about everything that fell into it? Does the information disappear forever? If so, this would violate the fundamental laws of quantum physics. This puzzle became known as the black hole information paradox. For decades, it divided physicists. Some argued that information is lost. Others proposed that information is somehow encoded on the event horizon itself. Ideas such as the holographic principle emerged, suggesting that all information inside a volume of space may be stored on its boundary. Black holes were no longer just astronomical objects. They were laboratories for the deepest questions about reality. Meanwhile, astronomers continued to find black holes throughout the universe. They observed powerful jets of particles launched from galactic centers at nearly the speed of light. They detected X-rays from accretion disks and measured the gravitational influence of unseen masses. Each discovery reinforced the idea that black holes are essential to cosmic evolution. Galaxies without active black holes behave differently from those with active ones. Star formation rates change, gas flows are altered, entire galactic structures respond to black hole activity. By the early 21st century, black holes were no longer controversial, they were central. Yet despite all this progress, something crucial was missing. No one had ever seen one directly. All evidence for black holes was in direct motion of stars, radiation from surrounding matter, theoretical predictions confirmed by observation. The idea of actually imaging a black hole seemed impossible. Black holes are small compared to cosmic distances. Even supermassive black holes appear tiny from Earth. Capturing an image would require a telescope the size of the planet, and then scientists decided to build one. For more than a century after Einstein's theory of general relativity, black holes remained invisible. Scientists could measure their effects, calculate their properties, and predict their behavior, but they could not see them directly. Black holes seemed destined to remain hidden forever, objects known only through equations and indirect clues. That belief did not survive the 21st century. The first major breakthrough came not through light, but through sound, cosmic sound, carried by spacetime itself. Einstein's theory predicted that accelerating massive objects should create ripples in spacetime, known as gravitational waves. For decades, these waves were purely theoretical. They were expected to be extraordinarily weak by the time they reached Earth, stretching and compressing space by less than the width of a proton. Most scientists doubted they would ever be detected. That changed on September 14, 2015, at exactly 9 hours 50 minutes and 45 seconds Coordinated Universal Time. On that morning, two detectors operated by the Laser Interferometer Gravitational Wave Observatory LIGO recorded a tiny but unmistakable signal. The detectors were located in Livingston, Louisiana and Hanford, Washington. Both registered the same signal within milliseconds of each other. The signal lasted less than a second, but within that fraction of time was encoded the collision of two black holes. Scientists later determined that the signal came from two stellar mass black holes, one about 36 times the mass of the Sun, the other about 29 times the mass of the Sun, spiraling into each other and merging into a single black hole roughly 62 solar masses in size. The remaining mass, about 3 suns' worth, was converted directly into energy and released as gravitational waves. This merger occurred approximately 1.3 billion years ago, long before multicellular life existed on Earth. The waves traveled across the universe for over a billion years before reaching our planet. On February 11, 2016, the LIGO collaboration officially announced the discovery to the world. It was one of the most important scientific announcements of the century. For the first time, humanity had directly detected black holes, not by seeing them, but by hearing the vibrations of spacetime itself. This discovery confirmed a major prediction of general relativity and opened an entirely new way of observing the universe. Gravitational wave astronomy was born, but an even more ambitious goal still remained. Scientists wanted to see a black hole. This challenge seemed nearly impossible. Black holes are incredibly small compared to the distances involved. Even a supermassive black hole billions of times the mass of the Sun would appear smaller than a grain of sand viewed from thousands of kilometers away. To see one, astronomers needed a telescope with the resolution of the entire Earth, so they built one. The Event Horizon Telescope, or ET, was not a single instrument. It was a global network of radio telescopes spread across the planet from Hawaii to Chile, from Europe to Antarctica. By synchronizing these telescopes using atomic clocks accurate 2 billionths of a second, scientists effectively created an Earth-sized telescope using a technique called very long baseline interferometry. The target was ambitious: the supermassive black hole at the center of galaxy Messier 87, located about 55 million light-years away. In April 2017, the ET conducted a coordinated observing campaign, collecting massive amounts of data, so much data that it could not be transmitted over the internet. Hard drives were physically shipped across the world for processing. It took nearly 2 years to analyze the data. Then, on April 10, 2019, at press conferences held simultaneously across the globe, scientists revealed the first ever image of a black hole. The image showed a glowing, asymmetrical ring of light surrounding a dark central region, the shadow of the event horizon itself. For the first time in history, humanity was not looking at an artist's impression or simulation. We were looking at a black hole. The image matched predictions made by Einstein's theory with stunning accuracy. The size and shape of the shadow confirmed the existence of an event horizon and validated general relativity under extreme conditions. It was a triumph not only of physics but of global scientific cooperation. But the story did not end there. The black hole in Messier 87 was enormous, about 6.5 billion times the mass of the Sun. Its size made it easier to image. The real challenge was closer to home. At the center of our own galaxy lies Sagittarius A, a supermassive black hole about 4 million times the mass of the Sun. Although much closer than the M87 black hole, Sagittarius A is far smaller and more active, making it harder to image. The ET team spent years refining their techniques. Finally, on May 12, 2022, they released the first image of Sagittarius A. Humanity had now seen the black hole at the center of the Milky Way. This achievement marked a turning point. Black holes were no longer theoretical objects or invisible monsters inferred from data. They were observable features of the universe, and yet the more we observed them, the more mysterious they became. Black holes challenge our understanding of time. Near the event horizon, time slows dramatically relative to distant observers. In extreme cases, time dilation becomes so severe that processes near the horizon appear frozen from afar. Black holes challenge our understanding of space. Inside the event horizon, all directions lead inward. There is no path back out. Space itself becomes dynamic, dragging everything toward the singularity, and black holes challenge our understanding of information. According to modern physics, information cannot be destroyed, but black holes appear to erase information by swallowing matter and eventually evaporating through Hawking radiation. This contradiction remains unresolved. Some theories suggest information is encoded on the surface of the event horizon, spread across microscopic quantum states. Others propose that black holes are connected to other regions of spacetime through quantum entanglement. Ideas such as wormholes, holography, and quantum gravity are actively explored. Black holes have become central to the search for a theory of everything, a framework that unites general relativity and quantum mechanics. They are not just astrophysical objects. They are philosophical challenges. They force us to ask questions that go beyond science. What is time? What is space? What is reality made of? Are there limits to knowledge? Black holes may even hold clues about the origin of the universe itself. Some cosmological models suggest that the early universe behaved like a black hole in reverse, expanding instead of collapsing. Others speculate that black holes could give birth to new universes, hidden beyond event horizons. These ideas remain speculative, but speculation is how discovery begins. From Einstein's equations in 1915 to Schwarzschild's solution in 1916 to Oppenheimer's collapse model in 1939 to the first strong observational evidence in the 1960s to gravitational waves in 2015 and direct images in 2019 and 2002 to the story of black holes spans more than a century. It is a story of patience, of imagination, of humanity pushing against the limits of understanding. Black holes were once considered impossible. Now they are essential. They shape galaxies, test theories, and redefine what we believe is possible. And despite everything we have learned, they still guard their deepest secrets. The discovery of black holes did not answer all questions. It revealed how many questions remain, and somewhere beyond space, beyond light, beyond time, those answers are waiting.